A very useful application of the dot product is in physics, and that's in work. The definition of work, we know work is force times distance, but actually what we mean is force in the direction that the distance is, that the object is actually being moved. And so an extended definition is actually this dot product, okay, where the force that's being applied to the object might not be in the direction that the object is moving. So we take that vector F that represents the force, do the dot product of it with S, which is the displacement vector, the vector that actually represents where the object is moving and how far. And that dot product is the work done by that force. And we can then apply our definition of the dot product, this alternative definition, using the angle and these two magnitudes. So this is a very powerful application of the dot product. Let's go ahead and see it in action. A force of 40 pounds on a rope is used to drag a box up a ramp that is inclined 12 degrees. If the rope makes an angle of 26 degrees with the ground, find the work done in moving the box 10 feet along the ramp. I'm going to go ahead and draw a picture here. I'll start by drawing the ground. Okay, the ground is just the flat, and then we've got a ramp, and the ramp is inclined 12 degrees. So let's say that this is the ramp here, and this angle here is 12 degrees. And we're dragging a box. Let's go ahead and draw the box. There's our box. And we're pulling a rope, and the rope makes an angle of 26 degrees with the ground. So I'm gonna draw it like this. Okay. Now this, if it was parallel to the ramp, it would be 12 degrees with the ground. So it's more than that, right? The rope is being pulled in that direction. And since I know that, I'm going to draw this little angle here. Since I know that the angle, oh, that was really bad. If I look at a flat, okay. So I know this angle here is 12 degrees, then I know that, and the full angle is 26 degrees, then I know that that angle right there is 14 degrees. Okay. Now, not sure if that really matters. Actually, what probably matters is just this 26 degrees. But that's what's happening here, okay? I am actually going to go ahead and just write that. I think that's what's going to matter to us anyway. This angle, this full angle, is 26 degrees. All right. Now this box moves 10 feet along the ramp. So now what we need to do is draw our displacement vector. So the force vector is this one right here. Let's go ahead and do that in red. So this is our force vector, F. And the displacement vector, that's, well, this box is moving 10 feet along the ramp. So that's this thing right here. Okay, that's our S vector. And we know then that we're looking for work, which is the dot product of those two vectors. So we need to find those vectors. Now, the vector F, I know the magnitude of F. It's a force of 40 pounds on this thing. So this is 40, but I need to know what this is actually a lot easier than I was initially thinking it was going to be. We're looking for F dot S, which by definition is the magnitude of F times the magnitude of S times the cosine of the angle between them. Well, the magnitude of F I have. That is 40. The magnitude of S I know. That's the distance that it travels, which is the 10 feet. And then I just need the cosine of the angle between them. Well, the angle between them, that's what I said before. I knew that this was 12 degrees, and to make up the 26 degrees, I knew that this angle was 14 degrees. So then I can go ahead and now actually evaluate this. Let's go ahead and plug this into our calculator. 40 times 10 is 400 times the cosine of 14 degrees. And that gives us 388.12. 388.12. This is work, which is measured in foot-pounds. We get that, of course, because the force is pounds and this displacement is feet. So that's feet-pounds.